Okay, we're now going to do a few examples involving rigid body kinetics. And so these will be problems involving forces and motion of rigid bodies, forces on rigid bodies, and the motion that those forces produce on rigid bodies. Okay, so here's some examples, and this is example number 1. So this is a pulley problem. But unlike our old pulleys so far in the course, this pulley is no longer massless. Okay, so pulley with mass. Okay, and this point G is the center of mass, and you have this rope being connected to this pulley and force F acting on that rope. Okay, so what's the setup? Force F equals 100 newtons. Pulley mass M equals, let's say, 1 kilogram. Pulley radius R equals 0.1 meters, let's say, and the pulley is a uniform disc. Okay, it's a uniform disc, and you're asked to find the angular acceleration of the pulley. Alpha, which is a vector, but it's going to be alpha scalar and in the k direction of the pulley due to force F. Okay, so how do we solve that problem? We use the equation sum of all moments, and we can take moments about G equals IG alpha K. So this is a single rigid body. It's a single rigid body. We can draw a free body diagram. There are three forces on this rigid body, one of which is this force F acting on it. Another is, well, the mass of the pulley acting down, and then another one is the reaction force R acting up. This is point G. So this is an FBD, free body diagram. Okay, you should always draw free body diagrams for these problems. And take moments about G, right? So take moments for this free body diagram about G. If you have a force that is passing through G, those forces do not produce any moment about point G. So the only force that produces a moment about point G is this force F. So moment about G of F equals, well, you can either think about it and just write it out. So it's going to be F times R, which is the moment term, F times R, that's scalar product, and then it's going to be anticlockwise. Anticlockwise moments are always in the K direction. So you can just write that down, F times R, K. Okay, so that's going to be the moment about G. Total moment about G. Okay, so that's the left-hand side of this equation. The right hand side is IG alpha. So FRK equals IG alpha K. So you can sort of ignore the case. And what we have is alpha equals FR divided by IG, which is the moment of inertia of the pulley. Which has been stated to be a uniform disk. It's been stated to be a uniform disk. If you look at the formula for IG for a uniform disk, it's m r squared by 2. So that's what that is. So plug that in there. So alpha becomes FR divided by m r squared divided by 2, which gives F over mr, and the 2 goes up, and you get 2F over mr. So that's alpha. Okay, and that's the answer. That's the angular acceleration. So there's a pulley. The pulley now has mass. A force acts on the pulley, and the pulley rotates because of the force, because of the moment produced by the force. And that rotational acceleration, or the angular acceleration, is basically the moment produced by the force, which is Fr divided by the moment of inertia, which is mr squared by 2. I computed the moment rather quickly by just saying it's F times R. If you want to compute it more formally using vector notation, computing moment using vector notation, let me do that separately. So first of all, notice that the force F is basically F in the minus J direction. So if you say this is J and this is I, the force F is basically in the negative J direction. So F equals negative Fj is something you can say. And the force F is applied at a point P here, let's say, which is this point. So Rp with respect to G, what is that point? So if you say you have a point G and you have this point P, this thing, if this is I, this thing is going to be minus Ri. So Rp with respect to G is minus Ri, right? So that's what this distance is. This distance is R. So from the vector from here to here, it's going to be Ri with a negative sign because it's going the opposite direction as I. So this is the this is the force. This is the vector from G to P. So the moment equals Rp with respect to G crossed with the force F, which gives minus Ri crossed with minus Fj. And these are, notice that these are cross products. Here, this is a cross product. You get Rf, I cross J, and you get FRK, which is what we used out here. Okay, so here we directly sort of said it's force times this moment term F times R in the anti-clockwise direction, which gives the K. That's a quick way of saying what the moment is. But if you want to use the vector formula, which is this, which involves a cross product, right? So that's a cross product. You can do that too if you want, which may be worthwhile for more complicated problems. For this simple problem, it didn't matter perhaps. Okay, so that's one problem. That's perhaps the simplest example involving rigid body kinetics. Okay.